Hello and welcome to the third Solfem v3 tutorial. In this tutorial we are going to create a beam 2D beam mesh with rod elements or truss elements. So let's get started. We open up the terminal window and navigate to the Solfem v3 work directory. From here we start up the script program.py and we select the viewer. So this is going to be a simple bridge example, very basic, just to show how to build it, how the program works. So first we will need a new mesh, and we can start by creating two nodes. So start making one at the origin and one at the coordinates -1 for x and -1 for y. Now click the nodes button to see the nodes. Okay. Now as in the previous tutorial, you can go in here and create the elements here, and I mean, yeah, sure, let's just do that now. Now between node 1 and 2, and we want a beam. We are not making a 3D mesh now, so we want beam 2N 2D. Okay, so here's our element between these two nodes. Now I'm going to make an arc. So first I select the element, and then I will click the Extrude Elements button. And we're going to use an angled extrusion. We're going to extrude in the direction in the 110 vector. That'll be our direction. And we will extrude 24 elements. 90 degrees about the axis -1. So the reason why we put -1 here is because of the right hand rule. So if it was 1, then we would be extruding in this counterclockwise direction. But when we put -1 here, it will become the clockwise direction, which is what we want. And let's put radius 12 here. Okay. And now we delete this original element. We don't need that anymore. So we can have a look at our element. So we can see here it's a 2D beam element. And next we are going to see, that's node number 1, and here we have node number 26. Well, actually let's create a new beam element between these two nodes by using the Insert Elements button. And what that does is it creates a beam element, but this is not a 2D beam element, so we have to convert this to a 2D beam element. So we can double check. Yep, now it's a 2D beam element. And let's split this element up into 16 elements. Yeah, this looks good so far. Now we have, these are about the same, and these and these. Okay, let's just select these nodes here, and we're going to copy these. And when you copy nodes, you just offset by a vector, and let's offset in the y direction 0.5 in the y direction. And the reason why we do that is we're going to use these to create new elements. We will select two nodes like this, and either you click the insert elements button here, or you can click I on the keyboard. So we'll do that for each of them. That's excellent. And we're also going to select all of them and create a node set from these. Node set number 1. Then we'll select these, there, and that'll be node set number 2. Now the reason why we are doing this is because these newest elements, they are going to be our truss elements. So we're going to convert these now. And let's make an element set while we're at it. Element set number 1. No, wait, convert them first. Okay, 2D rod elements. Okay, and I'm not sure if it matters, but let's recreate that element set just in case. And now we'll move these nodes down. If you remember, we offset them by 0.5, so 0.49 in the negative y direction. That'll put them right next to each other. And we'll offset these minus 0.51. Okay. Let's also create one node set over here, one node set over here, and we want an element set for all of our beam elements. Will be element set number 2 here. Also, actually, we're going to use these to apply our load, and we're going to use a distributed load here. So we will create nodes element set number 3 there. Distributed loads are applied to elements, not nodes. Okay, now we need properties for our elements, and we'll use carbon steel, newtons and meters and kilograms. on we'll call the first one beams section, and we don't need to fill in anything here because we will use this modify beam section. But let's also create rod section and carbon steel for that one as well. Now the beam section, let's make an I-beam. Let's make it 0.2 high. The width can be 0.1, both at the top and at the bottom. The top thickness can be 0.05. Same at the bottom, and the middle thickness can be 0.03. Yeah, okay, and this automatically calculates these properties that we need. And for the rod section, let's have a circle, and it's not going to be hollow. So if you put 0 here, then it's just solid. It's not the inner radius goes away, so it's just a rod. It's not hollow. Let's give it 0.05 radius. Okay, and we have to apply. We'll apply the beam section to elements. Which one was it? Element set 1 are the rods. Okay, rod section element set 1. Beam section element set 2. And we can see that now sections have been applied to all of the elements. And we're ready for our solution. We can click the static button. Let's just call it solution 1. Let's put a boundary condition on node set number 3 in the 1 and or x and y direction. So that's degrees of freedom 1 and 2, 0 displacement. And click this current solution button to highlight the solution. Next, we'll put 0 displacement in the y direction, so that's the second degree of freedom. And now we have rod elements here and beam elements here. The beam elements, even these are 2D beam elements, so they have 3 degrees of freedom in the x direction, y direction, and rotation around the z axis. But the rod elements only have 2 degrees of freedom at each node. So we're going to have to use a touch lock, or it's a multipoint constraint. So we made node sets of the rod element nodes and also of the corresponding beam element nodes. And the tolerance has to be big enough that it encompasses bigger than the distance between the 2 nodes you want to combine. So this is okay in our case. We want degrees of freedoms 1 and 2 to be locked for these elements, and this way these rods will now be hooked here, but they will not be fixed in the rotation because they don't have that degree of freedom. So the reason why we do it this way is because a node that is attached to a rod element only has 2 degrees of freedom, while a node that is attached to a beam element has 3. So those nodes can't be the same node. So we just have to have 2 nodes and lock them together in the degrees of freedom that we want. And finally, let's apply a distributed load on element set number 3 in the negative y direction. And let's just see here the distance 8.4. Well, it doesn't matter the distance. Well, oh yeah, 8.5. Yeah. Let's imagine this is a bridge with people walking over it. So let's say the average person is 80 kilograms and they occupy 1 meter. Yeah, let's say that makes sense. So that this will be force per meter. So 80 kilograms, that's roughly 8,000 newtons on element set number 3 in the negative y direction. And that's it. That should it should be ready now. Let's write the solution file. We'll add solution 1. Stress and strain are not available on beam elements, so we'll just not ask for those. And there we go. Writing sol file here, solution file 1.so. So the solution file is ready. We will click this run sol file in solver button, select the file we just created, sol file 1, and it runs here. There's a warning here you can see. If nodes don't have the same number of degrees of freedom, then you get this warning. It looks like it ran as expected. We can open the sol file.out file, and here we see new results are available: displacement, node force, and element force. So solution 1, oh yeah, the current result button there. Displacements, that looks reasonable. Makes sense. The load is applied here, it's pushing down. We can see the y direction. Yep, this part is being pushed down. And this part is being pushed up a little bit. So actually, if we increase this deformation scale factor, let's increase it a lot, maybe we can see, yeah, so that makes sense. It's being bent this way here, but downwards here. So that makes sense. That the displacements will be slightly upwards here, while downwards here. and it should also move in the X direction a little bit, maybe. Oh, it seems to be moving. We can probe the value actually here at this node. Probe node element info. The displacement, yes, it is moving almost nothing in the or well, actually 0.3 millimeters in the X direction over here. So yeah, looks like that makes sense. We can go on to the node forces. So these are the forces we applied. No, these are the boundary conditions were applied here. So as expected, it's being held up on the left and right hand side. Looks like 3,000, so that'll be 6,800, and we had 8.5 meters, 5 meters, and we had 800 newtons. So 6,800, yeah, that's spot on. The reaction forces are good. It also the forces between the multipoint constraints here will also show up as reaction forces. And we did not lock the boundaries in the rotation, so this should be 0. No reaction moments. And element force, so Fx, that'll be the axial forces in our elements, and here, as expected, we can see there is tension here. These beam elements are being stretched, and also these are being stretched. And of course our arch is being compressed. That's as expected. Fy, so these are the shear forces, shear force diagrams, if you want to look at those. And yeah, looks reasonable. Shear forces in the Z direction will not be there because these are 2D elements in yeah, these are 2D elements, so the Z direction does not come in here. Same with torsion, nothing, and bending about the y-axis, nothing, but bending moment diagram about the z-axis of our beams is available. So this looks correct. As we saw when we were looking at the displacements, this was it's being bent upwards here and downwards here. Similarly, it's being bent a little bit upwards here and downwards here. So yeah, it looks good. And of course you can probe element forces with the node element button, and this is useful if you want to calculate stresses maybe, or just want the element forces. So now you know how to combine rod elements with beam elements. And if you were to do this in 3D, then you would use beam elements, 3D beam elements and 3D rod elements, and you would use these same constraints to lock in the X, Y and Z direction, because you don't have the rotational degrees of freedom on the rods. So it's the same same method applied. Create two nodes, and one of them is on the beam, one of them is on the rod. And that does it for this tutorial. So I hope you found it useful. Thank you for watching, and have fun.